Alright, these are the Unit 3 practice problems for the Physical Science A exam. And just like the previous two units, I will walk you through the steps. It always is more beneficial if you actually work through them with me instead of watch me work through them. So I would suggest a calculator formula sheet. And we will jump right into it. So we start out with target 1 from the momentum unit. And so if you looked on your formula sheet, we know momentum is mass times velocity. That's important to remember. And we'll start out with the dog has a momentum of 200 units. Remember, the units are strange because it's mass multiplied by a velocity. So it just has a momentum of 200. What would it be if the mass stayed the same for the dog, but the speed was cut in half? So these are the thinking types of problems, where if we start out, all right, we've got a momentum of 200. Mass stays the same, so I don't need to do anything with that, but the speed was cut in half, or the velocity. So whatever we do to the right-hand side, we would have to do to the momentum, because those are direct relationships there. Whatever happens to one happens to the other. So if the velocity is cut by 2, the momentum is also cut by 2, which gives us a final momentum of 100 kilogram meters per second. Number 2, a bike has a momentum of 40. What would it be if it had half the speed but mass tripled? So let's think about that. Whoops, it's supposed to be mass. So momentum is mass times velocity. What would happen if it had half the speed? Let's start there. If we divide this side by 2, we also have to divide that side by 2. So now we have a 20. But mass tripled. So if mass goes up by 3, this number, now we're at a 20, would also have to go up by 3. Whatever you do to the right, you have to do to the left. So we divide it by 2, but then we triple it. We could have tripled it first and then cut that in half. It would not have mattered. 20 multiplied by 3 gives us a final momentum of 60. Number 3. What is the momentum of an object that has a mass of 20 and a velocity of 6? This is the easiest type. Momentum is just mass times velocity. So 20 multiplied by 6 gives us 120 kilogram meters per second. Alright, so that was the simplest target within this unit. And then the next mathematical target was number 3, which was this impulse momentum relationship. If you recall, lots of variations of it. All means the same thing. You exert a force over a certain amount of time, you cause that object with whatever mass, you cause that object to change its velocity. Alright, that's the impulse momentum relationship. What's important to remember first is how you calculate a change in velocity. This isn't like finding net force. Okay? If you are the floor, and here comes this basketball, it's going to hit you with a force of 9, with a velocity of 9, and you're going to push it back with 6. That's a total change in velocity of 15. So if somebody runs into you and they bounce off you, let's say, you have to stop them and then push them back. So you add those two vectors, those velocity vectors. So our change in velocity here is 15, which will be important later on. All right, so later on, this picture goes, I think, with number 5. Yeah. Okay, so number 4. What's the change in velocity of a ball if it hits the ground at 9 meters per second and rebounds off the ground at 6? That's this problem right here. Okay, so 9 plus 6, we already talked about it, 15. So using this picture, if I give you the force is 30 newtons, and the time of impact, so when the ball hits to it, gets pushed back off by the floor, is 1.25 seconds. You want to find the mass of the ball in kilograms, and we know from the previous problem its change in velocity is 15. The number one question people will ask is, which formula? After you get all your variables written down, whichever one has them in it, that's the one you use. So since we have a force, a time, we want a mass, and we have a change in velocity, it's this formula. And then we just substitute in 30 times 1.25 is equal to the mass times the change in velocity. So we're going to go 30 times 1.25, so 37.5 equals 15m. We're solving for m, so we divide each side by 15. So 37.5 divided by 15, answer is 2.5. So that basketball is approximately 2.5 kilograms. All right, number 6 says to refer to sled B. What is the impulse that would be needed to bring it to a stop? All right, so I told you essentially that B is the red one since you can't tell from my black and white worksheet. Impulse equals change in momentum. We could say that impulse equals change in momentum. People are like, well, I don't know enough. But if we also know that impulse then equals mass times the change in speed, we can get both of those from this. Because we know the mass of the Yeti, and we know that to stop this Yeti, we've got to bring 24 down to 0. So the impulse is the mass, which is 80, multiplied by the change in velocity, which is 24. And 80 times 24 is 1,920. Now the units are technically a Newton second because it's a force multiplied by a time. But what really matters is the 1920. Now, 7 and 8. This is where the charts proved helpful for some. And I'm not going to use a chart. I'm just going to make a list, but those charts will be available to you. And this is the elastic versus inelastic. One of the first things you had to do was decide if they stick together at the end of the problem, it's more inelastic. If they are separate at the end of the problem, it's elastic. So we start out, we've got a ball of putty going to the right. I even told you in this one, it's an inelastic collision. Another ball is coming to the left. They don't move afterwards, and we're looking for the initial speed of the 2 kilogram ball. So I'm going to just say object 1 is going to be this first one, and we've got to distinguish between them, so it's going to be the bigger one. Object 2 then is going to be the smaller one. So then, when you make your list, you've got to decide, okay, inelastic, so I have to use this formula. So I need all of these variables. Anything with a 1 subscript would go on the left. So M1, V1I, the initial speed. M2, V2I. Now these guys are going to share their final speed, so I'll kind of put it right on the fence here. They share those. So the mass of the big one is 4, the mass of the little one is 2. The big one is moving at 3 meters per second, and the little one is moving to the left. That's actually what we want to find, is the initial speed of the 2 kilogram ball. So that's going to be our x, and they don't move after the collision, so our final speed is 0. You might need to pause me to let all that process if I'm going too fast, because then I'm just substituting it into this equation. I'm not going to write this equation out right here. I'm just going to sub them in. All right, so you should be looking at it. So M1 V1I plus M2 V2I, that's what we're looking for, equals. Now they're combined at the end. That's why it's M1 plus M2. So 4 plus 2. And then it's multiplied by the final speed, which in this case is 0. So everything on that right side equals 0. 12 plus 2 V2I equals 0. Order of operations. We subtract 12 first. So we have 2 V2I equals negative 12. 0 subtract 12 gives you a negative 12. This is really just an x. It's what we're solving for. So if it was 2x, we know we would divide it by 2. Divide it by 2. Therefore, V2I equals negative 6. It is really, really important not to ignore that negative. It just shows that the other ball was heading the opposite direction, because the bigger ball of putty was moving to the right, The little guy was moving to the left. That negative shows a different direction. Number 8, we have a bowling ball. It's going down a lane, hits a bowling pin. We're looking for what speed does the bowling ball move off. So we're looking essentially for the rebound of the bowling ball. I think we've probably all had enough experience with bowling that we know that they don't stick to the pins, right? They're separate at the end. So this is an elastic equation. The table is almost the same. We pick one object to be object 1 and the other to be object 2. I'm just going to have the ball be object 1, the pin be object 2. It would be really, really smart just to pause me right now and see if you can do it. Okay, after going through the first one, there's not a ton of difference here. You look at all the subscripts that have a 1. You put them under the ball side. All the subscripts with a 2 go on the pin side. Just filling out what I know. That bowling pin starts at rest, so it's the starting speed of this pin is 0. We're looking for the final speed of the ball, and we know the pin moves off at 3. After that, then you look back at your formula sheet. This time we're using the elastic collision one. And so I'm just looking at that to make sure that I put everything in the right spot, so you should be as well. Give you a second for that. And then I would try to solve it. Okay, I would not just rely on myself here. Make sure you can do the order of operations correctly. This 1F is really just an X. Oops, V1F, sorry about that. So 6V1F. Remember, we add and subtract before we multiply and divide. So we have 48 is 6V1F. Divide each side by 6. Wow, nice even number there. So 8 meters per second is going to be the final velocity of that ball as it ricochets off. Alright, those are the practice problems from the momentum unit. The momentum unit tends to cause a lot of distress, so it would be pretty strategic for you to go back into Moodle and review your old attempts. Review especially the LT6s and then the LT3s and 1 attempts, because that's where a lot of the math is, and that was the more difficult part from that unit. All right, good luck.